to my Introduction to Remote Sensing in GIS course, everybody. Prepared and presented by yours truly, your local map aficionado at Soar. And we'll jump straight into the first little bit, which is, what is remote sensing, or our eyes in the sky? So what actually is remote sensing? Remote sensing is actually a combination of two words: remote, looking at something from a distance, and sensing is to actually observe it. So cumulatively, it's observing something from afar. And how that observing is actually done, it's from sensors, and they're usually installed on drones, planes, and what we are very familiar with is satellites. And those sensors sort of feed information of the observation, so whatever it sees, back to us in the form of imagery. And that imagery is actually made by detecting electromagnetic radiation that is received by the sensor. So it's not like taking photos exactly. So I'll touch a little bit onto what electromagnetic radiation is. So electromagnetic radiation is radiation within the electromagnetic spectrum. So within this spectrum, you've got stuff like gamma rays, you've got X-rays, you've also got the visible light spectrum. And the visible light spectrum is actually the light that we're able to see with our eyes. And that includes and within that electromagnetic spectrum, it includes infrared and radio waves, things that we get like our radio and TV signals from. And all of that radiation is within the electromagnetic spectrum, and the sensors actually pick up that radiation and feeds it back to us as imagery. Now, when talking about remote sensing, there's actually a couple types. So the first one is passive remote sensing. So it's passive because it receives the radiation or its energy source from outside of the sensor, more specifically the sun. So that radiation is actually sunlight. So because it depends on energy from the sun, it's very reliant on it being daytime. So it can only capture imagery during the day, and it cannot see through clouds because the clouds block the light or block the view, so you can't see what's underneath the clouds. And the common example of a passive sensor that we're very familiar with is Sentinel-2 satellites and Landsat satellites. They're both passive sensors. Now, there's a different type of remote sensing, and that is active remote sensing. So it's active because the sensor itself is actually producing the radiation. And as it produces radiation, whatever gets reflected back, that's what it senses. And because it's producing that radiation, it doesn't need to depend on sunlight, so it can be done at any time of the day, and it can see through clouds. Since that radiation can actually penetrate through the clouds. And a good example of an active sensor is actually a Sentinel-1 radar. So if you've been on Soar and in the Sentinel Hub tab at the bottom it says radar, that's a form of active sensing. It's because it's releasing radio waves down to the ground and receiving whatever reflections coming back up. Now, here's a visual example of what passive and active looks like. So this is passive remote sensing, Sentinel-2 true color imagery. So this is our good old Perth River, Swan River, and this is the same from a Sentinel-1 radar imagery. So you can see this one is very much representative of what we see with our eyes. This one, it's whatever, it receives the radio waves back and sort of images it to become this. So it's not really what we see, but it's a bit of a representation of what's on the ground. Now, when talking about satellites and sensors, we always talk about resolution, but it's actually a few different types of resolution when we're talking about sensors. The first being spatial resolution, second being spectral, third being temporal or time, and the fourth one being radiometric. So I'll touch on a little bit of each resolution in the next few slides. So the first one, which you'll be very familiar with, is spatial resolution. So what does that mean is the resolution is basically the dimension of what is on the ground represented in a pixel of an image. So if we're talking about 50 centimeter resolution, that means the pixel itself is 50 centimeters by 50 centimeters on the ground. And if we're talking about something that has a high spatial resolution, that means you could see more detail because that pixel, that representation is smaller, so 50 by 50. Now, this is a visual example of what I mean. We have SkyMap 50 here. It's got 50 centimeter resolution. You can see a lot of detail in the image, and you can really zoom in and see the different infrastructure there compared to Sentinel at 10 meters. So you can kind of see it, but not really as much detail. And then you have Landsat, which is the lowest resolution out of the three. It's only 30 meters, and you can barely see anything. Now, the next type of resolution I'm talking about is temporal resolution, or time. So basically, this means how often the satellite will revisit the same location. So if you're not aware, satellites are actually not stationary in the Earth's orbit. It doesn't just stay there. It's constantly moving around, capturing images. So if a satellite has a high temporal resolution, it means it can go around the Earth faster and come back to the same spot that it was at before. Now, a good example of this is comparing Sentinel and Landsat. So Sentinel can take 5 days to come back to the same location, whereas Landsat takes up to 16 days. Now, these are just two examples. Different satellites have different temporal resolutions, depending on how many is in its constellation. But these are just two very popular and more familiar examples that we see. Now, the next type of resolution is spectral resolution. So what does that mean? It means how good or how well a sensor is able to differentiate the sections of the electromagnetic spectrum. So remember earlier I had that bar with the gamma rays and the X-rays, blah, blah, blah. So if a sensor has a high spectral resolution, it means it can section off parts of that spectrum and identify what part of that spectrum is what type of radiation. And how you can usually tell if something has a high spectral resolution is by the number and the location and the width of the bands. So I'll touch a little bit on what satellite bands are later on, but here's a visual example of the differences in spectral resolution between a few different satellites. So the top here we have Landsat 8. As you can see here, there's like 1, 2, 3, 4, 5 just across this front portion of the spectrum, and then there's some at the back here. But then if you look at Sentinel 2, it's got more pockets of gray. So that means each of them are individual bands. So just on this graph alone, you could tell that Sentinel 2 has a higher spectral resolution because it's got more pockets of bands compared to Landsat 8. Now, we'll move on to radiometric resolution. So this doesn't really apply specifically to between satellites, but it's good to know when you're processing imagery. So radiometric resolution is essentially how sensitive the sensor is to the intensity of reflected electromagnetic spectrum. So a good way to put it is if a sensor has a high radiometric resolution, means it's better at differentiating or showing the different details in an image. So here's a visual example of what I mean. If something has like a 1-bit resolution, you can see it only has 2 levels. So it's just black and white. and I move on to something that has 2-bit with 4 levels, you can see there's a bit of gray, and you can see some contours in the hill here and a difference in the field here. Now, if you move up the resolution, radiometric resolution, to 8 bits, you can definitely see the different contours of the hills here. You can see the shades in the sky, and you can see the shades in the hill here. So comparatively, this has a lower radiometric resolution. This one has higher radiometric resolution because it can show more differences of detail in the image. So if you want to see subtle differences, you will want something with higher radiometric resolution, so you can really differentiate like the subtleties of what you're trying to observe. Now, can we have it all? Let's say you want high spatial resolution, everything you want 50 centimeters, right? And then you want high temporal resolution. You want 50 centimeters every day for the whole planet, every time. But you also want it in all the bands. So you want to be able to see it in radio waves, you want to see it in near infrared, you want to see it in everything, right? Is that actually possible? Well, the short answer is actually no. So why is that? It's actually a fine balance between spatial, spectral, and temporal. Realistically, you can only have 2 of these. So you can have high spatial resolution and high temporal, but you would get low spectral resolution. Or you can choose high temporal resolution and high spectral resolution, but you won't get a lot of detail in the image, so low spatial. So a good explanation as to why all 3 is not possible is really due to the transfer of that data from the satellite down to us. And that capability is quite limited due to the bandwidth of the data transfer, because something with a high resolution spatial, temporal, spectral, that's a lot of data you need to gather. And it takes time for that information to come back to us. So something that's captured at 11 o'clock this morning, we won't actually see it until tomorrow, because it takes that long for us to receive that information. And that's for something with low temporal resolution. So imagine if everything's high, how slow that will actually be. And on top of that, it's very expensive to maintain. You need a lot of tech and a lot of high advanced tech and a lot of bandwidth to actually receive that data. And it's just not really realistic or possible. And another thing is, not everything needs high resolution. You don't need high resolution everything of the whole world all the time. A good way to decide on what resolution you want to prioritize is to actually think about the information or the type of data you want to gather from your imagery or what you're trying to study. So if you want to monitor, let's say, if you want to monitor a wildfire, you probably want something that updates often. So something with high temporal resolution, and something that, if you want to see in more detail, probably something with high spatial. But that means you won't be able to see any thermal bands, or you won't be able to see any like near infrared or shortwave infrared bands. So there is like a compromise that you need to make, but usually that compromise is quite realistic to achieve. It's only unrealistic when you want everything at the same time. Now, we'll go and touch into the satellite bands now, since I've mentioned it briefly earlier. So what satellite bands are is basically what the sensors assign certain sections of the electromagnetic spectrum into. So you've got the whole electromagnetic spectrum, and then a band will coincide with a certain section. So it'll recognize a certain section of, let's say, red, green, blue, so on and so forth. And each band can actually have resolution that is different from each other. So you could have your red, green, and blue as a 10-meter resolution, but you can have something else as like 60 meters. But you don't have to worry about that as a user. Generally, all that data is resampled to actually match the resolution of the sensor in the final imagery product that you get. So most of the time you don't need to worry about it, but it is something to consider, especially if you're doing some deeper analysis. Now, a good visual representation is what I have here is Sentinel 2's bands and their resolutions. So you could see here in 10-meter resolution, you've got band 2, 3, 4, and 8. And then there's some in 20 here, so you've got band 5, 6, 7, 8, blah, blah, blah. And you've got 60 in band 1, 9, and 10 as well. So even though they are all in the same satellite, each band has a different resolution. Each band has a differing resolution, but eventually, once the data is captured, all of that is resampled down to 10 meters to match the important bits that we tend to focus on. Now, here's another example. This is a table of all the bands that Landsat has, Landsat 8 specifically. So you can see there's band 1 all the way to band 11. And then here you've got 30 meters, and then suddenly 15 meters resolution for panchromatic band. And then you've got 100 meters. But they all get resampled down to 30 meters. The next example I have again is Sentinel. So this is just a table version of that figure I showed you. As you can see here, there's like 60, 10, 10, 10, 20, 20, but it all gets resampled down to 10. Now, band combinations and ratios. So earlier I've touched on a little bit on when satellites give us information in form of imagery, it's not taking it in the form like a photo. And how that is done is actually through band combinations and ratios. So once that sensor has already detected that section of the electromagnetic spectrum, it will take that information of the radiation and you put it in different combinations, and then it'll produce that picture that we generally see. So like I said, it's a different combination of bands to convey specific information of the Earth. And band ratio specifically, it's pretty much a literal ratio. So you take band 1 plus or minus this other band, do some funky math to it, and then the output will be that image that you see. And that's usually done to highlight specific characteristics of the image, because different bands are used to look at different things. And doing that band ratio will specifically highlight things that you want to see. Now, a popular band combination that you would be familiar with is natural color and false color. So natural color here is a band combination made out of red, green, and blue bands. So this is what we will naturally see with our eyes because we have red, green, and blue cones. And then we have false color here, which is made out of near infrared, red, and green. Near infrared is in the red band pocket. So that's why everything just looks like it's red, because it's near infrared. Then you also have your band ratios, and some popular ones would be the NDVI and moisture stress. And you can see here the representation is a bit different than the combinations, and that's because it's an actual ratio. So you've got near infrared minus red, divide by near infrared plus red. So how it's done is actually whatever the value of that band is, it takes that value minus the value of a different band. It's quite literally math. And that output is visualized in this format. And this isn't like a color that we see. This is sort of set in GIS, which we'll talk about later on, to actually help visualize the output of that math. Here's another example, moisture stress. So this one's a bit different. It uses near infrared and shortwave infrared. Again, it's a ratio because it's got divided by something else. So again, it's math and it's visualized with colors. Now, this is the next part. What is GIS, right? You've got all that remote sensing data already, but you got to process it somehow. And that's where GIS comes in. So what does GIS stand for? It stands for Geospatial Information Systems. Now, Geospatial Information Systems. What that is actually a collection of computer systems that is used to capture, store, analyze, and display geographic information. So you got your remote sensing, which is capturing the images. And then the next step is actually using GIS to display that, to analyze it. Now, the main ingredient that we need is latitude and longitude. So the main part it needs is geography. So it needs to have latitude and longitude coordinates, because how else would we know where on Earth the information is about? So without that, we don't know where the image is or what it is or where it is, you know? Now, the next portion that's important in GIS is layering. Now, layering is actually a concept taken from maps, and you would be, if you're doing more creative work like in Photoshop or in GIMP, you will know about layering as well. Each layer helps build that final product, and that's the same with GIS. It keeps your information organized, and each layer is usually separating features of interest into like common groups. So you have a layer of roads, you have a layer of buildings, you have a layer of something else and something else. And then once you have all of that, you can actually start building relationships of each individual layer, because if they're all pressed together on one image, it's very hard to sort of identify or analyze it. But if you split it up into layers, it's easier to sort of form that relationships. And once you form that relationship, it's you can actually communicate different types of information or different types of data from that same like piece of data. Now here's a visual representation of this. We've got the real world here, but if you split that up, you can have a layer of land usage, elevation, parcels, streets, and customers. And from here, you can actually sort of build a relationship like, oh, there's all these customers here. Does that have any relation to the land parcels or land usage here? Or does land usage affect, like, does elevation affect the type of land that the land is used for? And you can sort of really like pull it apart and fully analyze why things the way they are. And it just keeps everything organized that way. Now, we talked about data, but we haven't talked about the type of data yet. So there are actually two forms of spatial data models. The first one being vector-based data. So vector is object-based, and it generally uses points, lines, and polygons. And it's great for accurate and defined boundaries. So something like rivers and roads and houses, specific locations, vector data is great for that. Then there's also raster data. So raster data would be more field-based, and it generally uses a grid or cells or pixels to form that data. So it'll be like a height of X amount of pixels, width of X amount of pixels, and each pixel has a different value, and it's represented in, and it's visualized in colors, and then it produces that raster image that we are familiar with. Here's a visual representation of what I mean. So we've got points, lines, and polygons, and these are all vector-based data. But if you change it to raster is very much like pixel-based. So roughly in this pixel is where this point is, so that's where the red pixel will be. And for raster line features, roughly here's where the line goes, that's where all the pixel is. So it will register the values and assign it into the pixels, and that's the visualization in there. Now, we've got that data, it has to be saved somehow, right? Now, remember, vector-based data is using points, lines, and polygons. Now, that generally is saved in these various file types. The one that we'll be most familiar with would be a keyhole markup language, or KML. So if you go on, so there's a little KML button. That's where you can import a vector file. And another popular one that we don't accept on Soar yet, but is widely used, is an Esri shapefile, or just shapefile. And generally, the one that we focus on is .shp. But when you create a shapefile, it generally creates a long list of other files along with it. So that's for vector. And then we have raster data formats. So remember, raster uses a regular grid of cells and pixels. So it needs to be field-based file type. So the one that we'll be most familiar with is like a GeoTIFF or an ECW. GeoTIFF is more widely used now. ECW is a bit of an older format, so it's not really supported in a lot of newer GIS applications, but it's still out there, and even on Soar, we still take it. Some other forms of raster data also includes PNGs, JPEGs, and JPEG 2000s. So they don't necessarily have geolocation to it, but it is still a form of raster data, because you would know like an image consists of pixels, and each pixel is trying to visualize something. So in essence, they are a form of raster data as well. Now, what can go on Soar-Earth? I think you all would know it is raster data. So something like that and something like that, they're all pixel-based and looks very impressive and pretty. And it generally lacks the defined lines and boundaries that you have in vector data. Now, I'll just zoom past this portion, because if I explain it too much, I think it'll be very confusing specifically for you guys. But essentially, since a lot, as a society, we've sort of transitioned a lot of our activities online, on the web. So naturally, maps have also gone onto the web as well. And with that, it needs to have these sort of web-based services to support spatial information. So the main form of data delivery that is very widely used in the industry is web feature service. So that service holds all of the data of that data set. And then how that data is actually visualized is through a different service. So that the most popular ones would be a web map service and a web map tile service. So I'll touch a little bit on those two in the next couple of slides. Now, a web map service, if you request for a web map service, it generally consists of these few main things. So it will always have a spatial context, and that will come in the spatial reference system. I'll touch on that a little bit later on. So this is usually defined by EPSG followed by a certain set of numbers. And it'll always have the extent of the map, so the outer four corners. And you'll also have the size of the image in width and in height. Then the next portion is a list of layers. So if that data set has layers, it will usually list out all the layer names, and will also list out the symbolization style. So if it has specific style the layer is displayed as, it will be written in that service. And then it will also say the return format. So if the data has a specific way that it can be displayed, it's usually listed here. So it could be in the form of a PNG, a JPEG. It'll also include other things like a background color and its exceptions. So some rules to how that information would be displayed. And here's just a map visualization of how it sort of works. So as a user, you'll request for a map here, and that GIS map data is actually imported into the server, and all that filtering and rendering and all that stuff is done within that server, and it gets outputted as a form of a map, which the user will actually see. So if we are requesting something, we don't see any of that. We just see this end result. Now, the next form of data visualization is a web map tile service. And that's what we are quite familiar with, especially on Soar. specifically a tile service is designed for high performance. So something like Soar, where people are zooming in and out all the time, requesting data all the time, it needs to be able to handle that speed of processing. So that's why a tile service would be more beneficial on Soar compared to a normal web map service. And usually how that is requested is by a set of rules. So you'll have a tile matrix set. Again, that's that spatial context CRS. It's defined by a column and a row. So how that is done specifically is you've got one big image here, and that is split into 4, and split some more, and split some more. And that each box is represented by like a column and a row. And that's how it gets requested, and that's how come it is able to load on the fly so quickly. That's because if you zoom into that portion, it'll just load that portion and ignore the rest, because that portion is what the user actually wants in that moment. Now, I've talked about a little about the spatial context. This is what I need. It's datums and projections. So that is the geographic information that we want to input into the image, right? So what is a datum? A datum essentially is a reference point that represents the position of real-world features. So you got an image, and you're putting like a dot on an image, and you're telling that dot on the image is what coordinates in real life. And the way that is sort of done, there can be many ways, and depending on what the map is, it can use a datum that is very specific to where that map is about. And there's like hundreds out there, so you can really pick and choose and be flexible on what you can what datum you can choose for your data. But the main one that we'd be very familiar with is specifically is WGS 84. So that one, I'll explain later why that is used. But for now, if you see all on Soar, it's this one, WGS 84. That's a bingo, the bingo datum. And then there's also projection. So a projection is basically a depiction of a 3D feature on a 2D surface. So it's very much like projecting, like if you're projecting an image, like you've got a thing and you're trying to lay it flat. Or a good example is you've got a round beach ball and you're trying to like stretch it out as much as possible so it lays flat on the ground and you can see all sides of that beach ball. And an example of some projections would be like a stereographic, Mercator, and Robinson. And I'll touch, but the one that we use on Soar will be Mercator, and I'll touch on later why that is used. Now, you'll probably be thinking, what is the difference? They both seem like they're saying the same thing. They're trying to describe a map onto like a map of a round thing on a flat thing, you know? Well, datum specifically is trying to give some form of location onto the surface of a round object. So you've got a map and you're giving it latitude and longitude for something that is already round. So that's Earth. And once you've already given that location, then it's projected. So you've already got that map that is laid on a round object. Then you want to project it to become flat. So datum is giving it information on something round, and projection is taking that round thing and putting it on something flat. And the reason datums, like when you're trying to give location to a round thing, there's many ways to do it, and it's usually based on like a mathematical model. And since there's a lot of math that exists out there, many ways to do it, that's why there are so many datums that exist. Whereas for projections, there's only a few ways you can lay something flat, because there's only a few ways you can do it without messing up how your map will look like. Because the last thing you want is for your map of a place to not look like the place anymore. You still want it to look like the place that you're talking about. So that's why there's only a few projections and a lot of datums. Now, what can go on SOAR? Specifically, what datum can go on SOAR? That would be the World Geodetic System, or WGS-84. The reason why that is used is because all of our GPSs actually use the WGS-84 datums. And the WGS-84 datum is actually made up of a reference ellipsoid, a standard coordinate system, altitude data, and a geoid. But the most important thing you want to remember for WGS-84 is that it uses the Earth's center of mass at the coordinate origin. So, coordinates is like a number, comma, number. For WGS-84, the absolute center, 0, 0, is at the center of the Earth. And because it's at the center of the Earth, it could cover basically the whole planet. And because we're a global platform, we're hosting information from all over the planet, we want something that could have information from every country on this planet. So using something that could accommodate that is very important. Now, in terms of projections, what we use on SOAR specifically, that's the base map you see in this background, is actually the Mercator projection. So what the Mercator projection essentially is that it takes our planet, our round Earth, and it stretches it out to a cylinder. And basically, it rolls out that cylinder into like a carpet. And this way, mostly this projection is picked because it looks the nicest. It's a flat rectangle that can be seen in a browser, and most of the features in the middle, they're more true to size. So most of the land masses actually are in the middle of our planet here. So since most of our land masses are there, you don't want any of the images to warp in this area. So that's why this projection is used. But the only drawback of this projection is because we're stretching the planet out into a cylinder, so the top portion here where there's less surface area is generally very, very stretched out. So you can see here there's like a big square there. That's because the representation, it's fully stretched out. So if you draw a square in Soar.Earth, like a square area, and you drag it around the base map, you notice the square actually changing shape from what you originally drew. That's because it's changing to the projection, to how the base map is stretched out. And this is just for visualization purposes. It is not changing how our planet actually is. It's just how we're able to sort of put a map onto a surface. It's purely so we could see things and contextualize our maps better.